that is only a qualitative proof. So now we want to perform a more rigorous, more quantitative analysis, right? So let me give you a very small value. And inside this value, we do have a non-vanishing magnetization vector. Okay, so in this small value, I do have lots and lots of magnetic dipole moments. And here I assumed I have current flowing in the counterclockwise direction, right? So if I have a counterclockwise flowing current, I produce a magnetization vector pointing in the x direction. So I'm using Cartesian coordinate x, y, and z, right? So the first thing is, well, how do you define its differential value? We're going to work from the definition, okay? So delta V is the differential value is placed in the denominator. So we have to find a way to formulate it. dx, dy, dz. Well, we're working in Cartesian coordinate. And what is your magnetic dipole moment? Well, your magnetic dipole moment is nothing more than I times the area, right? So we only care about this surface area. Surface area is dy dz, right? But the direction is pointing in the x direction. So in the x direction, the amount of current times the area, dy dz. So now we put this into the definition. The definition of magnetization vector is the amount of total magnetic dipole moments divided by the differential value. So this is pointing in the x direction and having the amount of I divided by dx, right? As I mentioned, it has a unit of ampere per meter. This is like a line current density. So basically, from analysis up to now, we can conclude we do have a surface current density, right? But looking at the figure, as we mentioned, JMS is more like a line current density. So this entire surface, like this surface marked by the yellow, is flowing with the effective current density due to the existence of this magnetization vector, right? But this direction is obviously not in the x direction, but in the z direction, right? This is in the z direction. So how do we formulate this one? Basically, the line current density is I divided by the length in the x direction, right? So this is I divided by dx, and in the z direction. So apparently, from your calculation of magnetization vector, the magnitude is identical to its line current density, but the direction, m is in the x direction, but your j is in the z direction. So apparently they don't match. But they will match once you perform the cross product of n to your surface normal. So the surface normal for this yellow marked surface is pointing in the y direction, right? So x cross y is equal to z, right? X cross y is equal to z, and you don't have a change in the magnitude. So this is a simple verification for that mathematical formulation, right? So once you induce magnetization vector, it produces the surface magnetization current density, remember its unit is ampere per meter, so it's more like a line current density. So this N cross AN, this is a surface normal, is indeed a valid description, right? Any questions up to now? No? All right. So that is a very simple proof. It's not a rigorous mathematical proof, but it is drawing out some value, and you have non-zero magnetization vector, and you can do the confirmation, right? So we have checked. This is okay. This is valid. All right, so next question is, well, we dealt with the surface magnetization current density, and now we're looking into the value. Well, if you still remember, the volume magnetization current density is having the curl operation of M. First, you have to think, what is curl? Well, curl is trying to find the circulation, right? So therefore, you have to form a closed loop, and you find the net circulation. It is not zero, and you have an effective value magnetization current density. So the first question you have to ask is, when can this value be non-zero? In the current case, we have a very uniform magnetic material. Uniform means, well, homogeneous. Let me use a more correct term. A more precise term would be, what I'm trying to draw out now is a very homogeneous magnetic material. Homogeneous means each point in space gives you the same amount of magnetization vector. Right? Homogeneous means it's uniform in space, so all the results is not space dependent. So in this case, point by point, as we discussed, point by point, you have no net current. How can you expect the entire volume to show up with a net current? That doesn't make any sense, right? So if you perform the curl operation for this material, you don't even need to calculate it. It's zero. Because point by point inside, all the currents are canceled out by the adjacent loops. You don't even need to calculate. So when do you expect to have a non-zero value magnetization current density? When do you expect to have the curl of N to be non-zero? If this N vector is a constant, it's not spatially dependent, curl operation must be zero, right? What do I mean? If this N is some N0, a constant, curl operation performs differentiations in x, y, z, right? Constant gives you a zero differentiation, right? So the only possibility is, well, we are dealing with an inhomogeneous magnetic material. Inhomogeneous means, well, maybe for this loop, the magnetic dipole moment induced here is stronger as compared to this location, right? So even though the current directions are all the same in the counterclockwise direction to confirm that your induced magnetic dipole moment is aligned to your externally applied field, but the magnitude can be different. Right? So now you think, well, at this location, at this point, do you have a net current? You do. Because, for example, for this one, it has a 5 unit of current flowing downwards. But from this green one, you only have 1 unit of current flowing upwards. So basically, you have 4 units of current flowing downwards. Now, in this case, you expect this entire value to show up as a current source. And that relies on the fact you have inhomogeneity, spatially non-uniform. Then you can have a bulk material giving you non-zero current. Okay? So that is the meaning of the curl operation. If this curl is not equal to 0, which means your material is inhomogeneous. Just like the case we discussed for the volume charge density for dielectrics, right? You need to have inhomogeneous material to give rise to a non-zero volume magnetization current density. Okay? So let's look at, well, a really inhomogeneous material in a microscopic sense. So over to the left, you have a stronger magnetic dipole producing material, and over to the right, you have a weaker one. So I'm using 3 current loops and 2 current loops to reflect that fact. So with the same externally applied magnetic field, the left one can give you 3 units of magnetic dipole moments, but over to the right, only 2. Now we form a closed loop, right? A surface. And we ask ourselves, what is the net current penetrating this closed surface area C? Well, we can write this. I defined this location as x, and this is x plus dx, right? So I want to know the net current passing through this contour. So the Ix minus Ix plus dx, that is the net current. But as we all know, M, the magnetization vector, has a unit of ampere per meter. So all I have to do is m of x minus m of x plus dx. I'm evaluating the magnetization vector here and here. The difference multiplied by what? By this dc. By dc. That is equal to the net current. Right? So the current density is basically I, the net current, divided by the surface area. Right? Surface area is dz times dx. And I know the currents are in the y direction, right? Into the paper or out of paper, but in any case, it's in the y direction. We already know how to formulate the net current. Right? So in the end, the volume current density is in the negative y direction, and this is basically the differentiation of m in the x direction, right? But remember, the ends m of x and m of x plus dx are oriented in the z direction. So basically, you're performing partial differentiation of the z component of m with respect to x. This is not a simple derivation, okay? So it conforms to the curl operation, right? So this is not, again, not a very rigorous proof, but this shows you, once you see this formula, and if you're brave enough to understand, you need to have inhomogeneous material, meaning at this location and at this location, they actually give you different strength of magnetization factors. And you form a closed loop and you do the calculation by the definition, you can verify this is indeed true. This is a valid mathematical description to the induced value magnetization current density. Okay? All right, so that's checked. So time is well controlled. Let's take a look at one particular example. If I have a material, it's a cylinder-like material and it's magnetic, since the geometry is cylindrical, of course, I want to use cylindrical coordinate system to describe it, right? So the textbook asks you, well, if this material molded in the cylinder is giving you a constant, well, if you look at this constant magnetization factor, you will be very happy. Why? Think about it. This material, the cylinder, is having a non-zero magnetization factor aligned in the z direction, but it's a constant. So everywhere, inside, everywhere, you have the same magnetization factor. Why would you be so happy? Because you know, in this case, you're dealing with a uniform material. Therefore, you don't even have to perform the curl operation, meaning this material does not give you a volume magnetization current density. Right? You don't have the volume current density, and therefore you only have to care about the surface current density. You only have to care about the surface current density. But then the question is, how many surfaces do you have? For the cylinder, you have the top lid, so that is surface number 1. You have the bottom lid, the bottom surface. And then you have the third surface, that's the circumference, right? Now think about it. Eventually, the surface magnetization current density is making the cross product with the surface normal. So in this case, n is aligned in the z direction, right? So your n is in the z direction, but your top surface normal and bottom surface normal both are also in the z direction. So z cross z is equal to 0. Which means, in this case, even though you have surface number 1, surface number 2, and the third, the circumference surface, the top and bottom do not contribute to the surface current densities. You only have to take care of this surface, pointing outwards everywhere. Okay? So basically, you perform n cross an. In this case, the surface normal everywhere on the cylindrical surface is pointing in the radial direction. So you have a z direction M0 as a constant, making a cross product with AR. Z cross R is phi. So the resulting surface magnetization current density is pointing everywhere in the phi direction and with a magnitude of M0. So what does that mean? That means you can actually view the cylinder as lots and lots of current conducting loops with differential height of dz prime. So you have one loop here, another loop here, you increase the height of the loops. Okay? So this is equivalent to a huge current conducting loop with total height of F. But you can decompose them into lots and lots of small current loops, each with a height of dz prime. So why is that important? In the end, we want to know what is the total B field created by this magnetic material at an observation point of 0, 0, z. Well, if you still remember, we actually analyzed a simple case, right? For a simple current conducting loop with current I, and our observation point is 0, 0, z, same here. We already know the result. So if I have only one current loop, I know this is my end result from our previous example. So now the situation is we have lots and lots of this current conducting loops, but each one having a different distance to my observation point. So all I have to do is for each equivalent current conducting loop, I have this much amount of current, M0 times dz prime. That is the current conducted by this differential loop. Okay? And I have to take care of the proper distance from my observation point to its own z location. And that's it. And then I integrate z prime from 0 all the way to L. And that's it. Okay? So this is finding a real connection to your previous example, right? So once you have a uniform z-oriented magnetization factor for a cylinder, you can view it as a series of differential current conducting loops, but each one is having a different z value. So the end result is simple and straightforward. Right? So again, a quick conclusion. Once you have magnetic materials, you have the ability to create lots and lots of magnetic dipole moments. But if you have a uniform magnetic material, inside of it, you don't really have net current because the currents will be canceled out by adjacent loops. So you only have the surface current. In this case, you only have the surface current at the outer edge, right? So unless you have a non-uniform magnetic material, otherwise you always have surface currents. Okay? So if you have the volume current density, that means your material is suffering from non-uniform in terms of space, right? All right, so let's conclude for the day. Next Monday, we are going to define the difference between B and H. So it's better for you to preview the course contents before coming into class. Alright, thank you. Let's stop here.